Hello, my name is Blake Moddelmog, and I'm going to be discussing and going over a drag problem. So it says that the aerodynamic drag of a new sports car is to be predicted at a speed of 50 kilometers an hour at an air temperature of 25 degrees Celsius. Automotive engineers build a one-fifth scale model of the car to test in a wind tunnel. It is winter, and the wind tunnel is located in an unheated building. The temperature of the wind tunnel is about 5 degrees Celsius. Uh, and we're going to be going over part A here, determine pi terms involved in this analysis using MLT basic dimensions. So starting off, I just wrote out some of our givens. That's going to be more helpful in part B and C. So we're just going to ignore that for now. And with the pi terms, to find those, we're going to want to use the Buckingham pi theorem, which will give us the pi terms. So to do that, we're going to need variables. Thankfully, we have them here. We have uh, drag force, length, density, velocity, and viscosity. So we have our variables out here. And to find out how many pi terms we're going to be solving for, we need to find the number of terms, which we have, which is 5. And then we need to find what dimensions we're using, the quantity, which will be 3. And then we subtract the number of terms from the number of dimensions, which gives us 2, which means we will be finding 2 pi terms. So we know that for drag force, all of the other variables are going to be used to find it. So drag force is a function of length, velocity, density, and viscosity. So for Buckingham pi theorem, we're going to need to find the repeat dimensions. And to do that, it needs to follow 2 rules. The dimensions can't cancel and they can't be dependent. So here we have length, velocity, and density. And as you see here, the dimensions, when combined, do not cancel out to form a dimensionless parameter. And coming back here, they can't be dependent. So what I don't have listed here, drag force and viscosity, are dependent. As you can see up here, the drag force is clearly dependent with all these variables, and with viscosity up here, it is dependent on temperature. So we leave those out, and we have our repeat dimensions right here. So to start off with the first pi term, we're going to want to multiply one of our dependent variables. Let's just choose, I chose viscosity. And we're going to multiply that from to our repeat parameters, each with their own variable in the exponent. And we're going to be solving for those variables. To start that off, we're going to want to come down and up here, actually, I wrote out the dimensions for all of the variables used. Length is length, easy enough. Drag force is mass times length times time to the negative second, and keeps going. And here we use viscosity, so mass over length times time, and multiplied by these plugged in here to A, B, C power. And to find A, B, and C, we're going to want to set this equal to m to the 0 times L to the 0 times T to the 0. And then from there, we want to take each dimension, mass, time, and length, and uh, set them equal to 0 as we did here. So we're going to want to bring the 0 from there is equal to 1 plus c. Where did I get that from? Well, if you start here, mass is to the first power. So we're going to put 1 here, and it's not anywhere else except for right here, which is m to the c. So we're going to have c here. We're just bringing down the powers. So 0 is equal to 1 plus c. So c is equal to negative 1. Then following suit, we do it with time. 0 is equal to negative 1. See that? Bringing a negative 1 power down here. And then it's going to be t to the negative 1 times b, which is going to be b to t to the negative b power. So that's going to be 0 is equal to negative 1 minus b. b is equal to negative 1. Just doing the same pattern here for length. 0 is equal to minus 1 plus a plus b minus 3c. We're taking the negative third power, multiplying it by c. So we just get that out, we plug in the negative ones, and funny enough, we get -1 as well. So all of our variables are -1. So when we just plug that right back in to right here, we're getting mu times L to the -1 times V to the -1 times rho to the -1. So our first pi term is viscosity over length times velocity times. And we're just doing the exact same thing here for the second pi term, except we're switching out the dependent variable, which from viscosity to drag force. Notice we're keeping all the same length, velocity, and rho right here. So our answers will change due to the dependent variable having different dimensions, as you can see here. And then we're going to just follow the same process here, bringing down our mass, time, and length. And I like to do it in that order because usually length has the most variables in it. It shows up quite often in dimensional analysis in most terms. So I like to leave that for last, and I start with mass. And we're just doing 0 is equal to 1 plus mass. So 1 plus c over here. That's the only other time mass shows up. So it's 1 plus c. C is equal to -1 again. Plugging that back into time, or going to time, we're seeing that 0 is equal to -2 minus b. B is equal to -2, simplifying that out. Then we bring it back to length, c, because we have all the variables in it. So thankfully we have them right here. 0 is equal to 1 plus a plus b minus 3c. And plugging in the variables we already have, we get a to be -2. So plugging it back in here and then simplifying it in one fraction, we get the second pi term is equal to drag force divided by length squared times velocity squared times density. And that solves part A with our 2 pi terms. All right, so moving right on to part B, it asks that determine how fast the engineer should run the wind tunnel in order to achieve similarity between the model and the prototype. So for that, we're going to want to remember our givens here, especially the model to prototype ratio. And we will be needing to find the velocity of the wind tunnel, which will be the velocity of the model. So going down to we're going to want to be using the pi term that we found. Now, it doesn't look too familiar. It's the one that we see here is going to be viscosity over length times velocity times density. But if you flip it upside down, switch the numerator and the denominator, you're going to actually find Reynolds number. So we're going to keep it just like this. It doesn't really matter. It's the same ratio if you flip both of them either way. We're going to keep it like this. And what we know about Reynolds number is that for the prototype and the model, they're going to be equivalent. So we take these values and we take the just flipped Reynolds number for the prototype and have all the values prototype, 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 and make it equivalent to the model's version. So doing that, we just use some algebra and get we use this proportion or equality and get it to V model, which is what we want to find, the model velocity, and find it equivalent to everything else, which is just going to be the model's viscosity divided by its length times density times the prototype's length times velocity times density over viscosity. And we're going to input all the values we have here. We found these viscosity values up here. Remember, the 5 degrees is the model and 25 degrees is the prototype. So we have the density here and the viscosity for the prototype and the model's density and viscosity. So we pull those values down and we plug them in, and we want to take the length of the model and the length of the prototype and make them their own fraction, because we know that there is a relationship between the size of the prototype and the model in this in this example, it's length, because that's the dimension we have. So the length of the prototype divided by the length of the model is going to be 5, because if you see here, the length of the model is 1/5 the size of the prototype. So if you do prototype in terms of model, it's going to be prototype is equal to 5 times the model length. So bringing it back, we have this is equal to 5, and then we are going to multiply it everything out. We have 50 here. That's going to be the velocity of the prototype. We have the density, the lengths are here, viscosity, that length here, and the density down here. And that's going to come out to 221.27012 kilometers per hour as the velocity of the model. All right, so finishing it up with part C, says that to suppose the engineers run the wind tunnel at 221 kilometers per hour to achieve similarity between the model and the prototype. The aerodynamic drag force on the model car is measured with a drag balance. Several drag readings are recorded, and the average drag force on the model is 35 newtons. Predict the aerodynamic drag force at the initial conditions given. So we're going to take this and this. This was pretty close to our answer from part B. This is just the simplified version, less sig figs. And coming down here, we're going to want to find we're asked to find the drag force of the prototype. So we're going to be using our equivalent pi terms. And this is going to be the other one, the one that includes drag force. So we're going to want to set them equal to each other as the theorem goes. And since they're equivalent for the prototype and the model, and we're going to want to simplify it to just get the drag of the prototype. So we're going to keep this here, multiply both sides by the L squared times velocity squared times rho of the prototype, get that over there. And once again, we're going to drag out the prototype and the model. Both of these are squared, so we're going to pull out that squared. And as this simplifies down to 5, same as last time, it's going to be squared. So from there, we just plug in the values. We're given the drag force of the model, and we are given the velocity of the model as well. All of these have already been given, and we just multiply out, and our final answer is 41.788193 newtons as the drag force of the prototype.